Yeah, thanks. Am I audible on the mic? Yes, okay. So, thank you for the invitation. It's great to be here. As Krista mentioned, I'm local, so it's also nice that I could cut down on registration costs by limiting travel expenses. I want to talk about something that I personally find very exciting and honestly an area in which progress now has slowed a bit, and it's pretty clear that that we need experts in quantum information theory and quantum computation to push the progress forward. So let me start sort of back at the beginning, combinatorial optimization. I know there's a varied background of people in attendance. So let's look at one of the classical problems in theory of computation, which is the traveling salesman problem. So you're given n cities and some costs to travel between them, and the goal is to minimize the cost of travel, visiting every city and returning to your starting point. Okay, so like here's a picture of a tour on 7 vertices. The blue highlighted edges are the tour, and and so if you're given a cost function, you can think about finding a tour that minimizes the cost. And that's a classical NP-complete problem. And well, here's a quote from Giancarlo Rota, which is that sort of the theory of polyhedra lay untouched since the time of Archimedes until these computer scientists started studying discrete optimization, and then sort of the field made a bit of a resurgence. And I guess if you're somewhat younger and you don't remember Archimedes, then there was also a hit Hollywood movie about the traveling salesman problem that came out a few years ago. Okay, so now the movie poster is blocking Giancarlo Rota's quote, but it was very prescient because indeed most of our understanding, or a very significant piece of it, of the traveling salesman problem comes from understanding polyhedra. So by the way, if you're not familiar, this thing over here is a picture of a polyhedron. It's just the convex hull of a finite set of points in Rn. And the way that it's related to the traveling salesman problem is you can associate a very natural polytope. So think about all the points in n choose 2 dimensions corresponding to subsets of edges in the complete graph that are tors. Okay, so take all of the indicator vectors of tors. So you just put ones on the edges of a tor and take their convex hull. That's the TSP polytope. And the reason that in computation we care about polyhedra is because, there's a very rich theory of linear programming which says that we can optimize linear functions over polytopes. Now, TSP is an NP-complete problem, but now here we've written it as an optimization over a polytope. So, given the costs, it's not hard to check that the optimal solution is the minimization of this linear functional over the TSP polytope. And so now you can ask, why doesn't this prove that P is equal to NP if we have efficient algorithms for linear programming? And it's because sort of the generic algorithms for linear programming, say, based on interior point methods, they run efficiently, but it's time polynomial in the number of facets of the polytope. So the facets are the faces of highest dimension, sort of for this 3-dimensional polytope, the 2-dimensional faces are the number of facets. And okay, this is not unexpected. The traveling salesman polytope has exponentially many facets, and therefore, you can't just plug this thing into an interior point method solver and expect to get something efficient. And in general, you could tell the same story for many NP-complete problems, and it's not particularly surprising. Okay, you can't solve them by linear programming. You can't prove P is equal to NP just in the obvious way. But if you started this story a little bit differently, say with the minimum spanning tree problem, okay, so there you again have n cities and costs between the cities, and now your goal is to find, instead of finding a tour, just a spanning tree. And from undergraduate algorithms class, actually we know this problem is actually in P. There's a polynomial time algorithm. There's I jumped the gun there. There's a corresponding, polytope, which is the convex hull of all the indicator vectors of spanning trees. And since this problem is in P, you might expect that the story would have a different end. But no, again, this polytope has exponentially many facets. So far it doesn't seem like we've gotten anywhere. But it turns out that the complexity of this polytope is just an illusion. This polytope is actually the shadow of a much simpler polytope sitting in a higher dimensional space. Okay, so it's known that the spanning tree polytope has a lift in n cubed dimensions that has only order n cubed facets. So the polytope itself has exponentially many facets, but it's the linear projection of a polytope with only a small number of facets. And as I'll say on the next slide, that if you can optimize over the lift, if you can optimize over the polytope upstairs, you can optimize downstairs. So, I mean, this is it's a cute structural result that you can write the spanning tree polytope as a projection of something much simpler in a higher dimensional space. But actually, if you think about the algorithm that this encodes, it's something very sophisticated, because what it basically says is you can pass to a higher dimensional space, and then you can define a geometry on this polytope upstairs so that continuous optimization, gradient descent, upstairs actually leads you to a solution of a combinatorial problem downstairs. Okay, and in general, sort of based on this idea, you can define sort of a general theory of, say, linear programs and linear programming relaxations of polytopes. So here's the formal definition of a lift. It's just what I said. A lift of P is a polytope that linearly projects to P. And it's not hard to check that if you can optimize over the upstairs over Q, then you can optimize over P. Okay. Just as a note, from the point of view of people designing linear programs, sort of the number of facets in the lift corresponds to the number of inequalities, and the lifting process itself just corresponds to adding new variables to the linear program. Okay, so you're adding new variables, gives you some more expressibility, and it might be the case that with many fewer inequalities now you can express the constraints you were trying to express. So now there's a whole field devoted to studying this. So it makes sense to talk about not the intrinsic complexity of a polytope P, but it's in its natural representation, but its extension complexity, which is the minimum over all possible lifts of P. So the extension complexity of a polytope is small if it's the shadow of a polytope with a small number of facets. And then we have lots of examples where you can get an exponential savings by passing to lifts. So where the natural polytope underlying a set of combinatorial objects has exponentially many facets, but these things are shadows of simpler polytopes. Let me mention two things. First of all, this is a remarkably powerful model of computation, especially when you allow approximation. I'm not going to talk about approximation very much, but you can imagine what it means in terms of lifts. You would like to say project inside the body downstairs, and then if you enlarge a little bit upstairs, you would like to contain the body downstairs. And then that's not quite an accurate description of what you should do, but it's close enough for the sake of the talk. And there are actually entire books on approximation algorithms via linear programming, where really the books are just studies of this model of computation and their application to getting close to the solution to NP-hard problems. So it's a very powerful model. On the other hand, if you don't expect that P is equal to NP, you don't expect that you should be able to prove P is equal to NP. So if you had, for instance, small lifts of the traveling salesman polytope, that would essentially show that something a little bit weaker than the fact that P is equal to NP. So you don't expect that they exist. Okay. So this field is goes by the name of extended formulations. And let me just give you a very brief history of what happened there. This is very truncated, missing 50, 100 references. But in the 80s, there was a fellow. It's not a person named fellow. It actually means like a fellow. I feel like he got enough bad press, so I'm not saying his name anymore. He tried to prove that P is equal to NP by giving a small linear programming formulation of the TSP polytope. So it had n to the 6 constraints. He sent it to stock. The referee, obviously, it was a paper that people wanted to find a bug in it. The referee found the bug. The paper was rejected. And then in the next stock, he sent an updated version with a linear program that had n to the 12th constraints, again claiming that P is equal to NP. Again, the referee found the bug, and the paper was rejected. And something really remarkable happened. So Mihalis Yannakakis was the referee, and he just proved that actually such an approach could never work to prove that P is equal to NP. So he showed that no symmetric linear program for TSP can have polynomial size. And all of the things that this fellow was trying to do were giving symmetric linear programs. I feel like this is sort of a little bit unheard of, and maybe maybe we can't do this anymore because we're afraid of like approaching P versus NP. But it's not usually the case that you can prove an unconditional lower bound in a computational model where there's lots of interesting algorithms. So this was, I think it's a really impressive thing that Mihalis did. So then about 20 years passed, and a different set of people attempted to prove that P is equal to NP, but now giving an asymmetric family of linear programs for TSP. Okay, so I'm not saying what symmetry means, but it's basically that the programs respect the underlying symmetry of the TSP problem when you permute the cities. And then just shortly after that, in this fantastic paper of Fiorini et al., which I believe that I think Ronald talked about at QIP a few years ago, showed that actually Yannakakis' result can be extended to any linear program. So the traveling salesman polytope does not have any small subexponential size LP formulation. And it's a bit of a joke here because it would seem that crackpots are driving scientific progress, but I'm pretty sure that that Ronald and friends were not motivated by the 2011 preprints. Okay. So let me mention two more results in this area. So a couple of years ago with Suan Chen, Prasad Raghavendra, and David Steurer, we proved that that actually there are some problems, some natural problems that polynomial size LPs cannot solve, even though small SDPs can solve them. And so one problem one such problem is max cut. In this model, no polynomial size linear program can get better than a factor of 2 for max cut, which is kind of a trivial bound. What I mean is compute a solution which is better than within factor 2 of optimal, even though the famous SDP algorithm of Gomans and Williamson can do much better. Okay? So this is nice. It gives some gap between the power of linear and semi-definite programs. And then, clearly progress is very fast here. A year later, actually, Thomas Rothfuss really completed Yannakakis' program. This is sort of I think the ultimate thing that Yannakakis would have liked to prove there, which is that even the matching polytope does not admit subexponential size LP characterizations. And if you're sort of a history buff of computer science, this is pretty fantastic because the P versus NP question, I mean, one of the papers that really sort of started to cement it in people's minds was a paper of Edmonds on the matching polytope, where he showed that matching actually has a polynomial time algorithm based on using an exponential size LP formulation. Okay, so really this this field is okay, it's in good shape, and there's a natural question if you hang around in these circles, which is what about semi-definite programs? So now, first of all, you don't have to know what a semi-definite program is. Let me tell you what the model is and try to tell you why it's an important question. Okay, so let this SK be the cone of K by K positive semi-definite matrices. And then a spectrahedron is the intersection of this cone with some affine subspace. Okay, so here's a picture of a spectrahedron. This is the elliptope. Sits in 3 dimensions. So spectrahedra are precisely the feasible regions of SDPs. This is not a polytope. If you can see, I mean, you can see that it's curved as you would expect. The cone of positive semi-definite matrices, it's not bounded by some finite number of hyperplanes. And then you can define a sort of a corresponding theory, which is that the PSD lift size of a polytope is the smallest spectrahedron that projects to that polytope. Where I'm measuring things in terms of this parameter k. I will call k the dimension sometimes, perhaps on accident, even though the dimension of this space is really something more like k times k plus 1 over 2. But okay, so it's easy to see that this model is more powerful. So with PSD lifts, you can implement all of the polyhedral lifts. There is a reason that semi-definite programs are special. Well, there's a reason we think they're special. Assuming the unique games conjecture, which is this sort of one of the major open problems in complexity theory. If semi-definite programs cannot solve constraint satisfaction problems like max cut and max 3 set, actually under this conjecture, there's a way to take this hardness against one particular model and convert it really into computational hardness, which says that no efficient algorithm can do better. So this is sort of a powerful connection. It's conjectural between SDPs and all of efficient computation. And okay, and sometimes you can do better for polytopes with SDPs than with linear programs. So actually, the elliptope here is one example. If you project it, okay, it's not really down, it's to the side. It doesn't matter, everything is symmetric. It's just so I didn't want it to block your view. This thing actually projects to the unit square. The unit square has 4 facets. This polytope, and that's the best you can do with a polyhedral lift. And with an SDP, you can do something of size 3. You have a 3-dimensional SDP. Okay, so at least there's a gap of 3 versus 4. There are gaps that grow. Sort of you can as sort of so there's a okay. So here you should, instead of D, you should think of N. So there are gaps that grow with N, the parameter of the underlying problem. But the real power of these things, where we know that significant gaps exist, is that for approximation problems, now we know that SDPs can be exponentially more efficient than linear programs. So for max cut, in this recent work of Kothari, Mecca, and Raghavendra, they showed that no sub-exponential size linear program can do better than factor 2 for max cut, even though the Gomez-Williamson SDP gets much better than factor 2. Okay, so now the question that you might ask is, okay, can semi-definite programs prove that P is equal to NP? Again, it's a very powerful model of computation. The methods for linear programs for understanding their power didn't seem to work, at least after a few years of effort. Okay, and so that's the main thing I'm talking about today, which is that it's not the case. So SDPs cannot prove that P is equal to NP. So this is joint work with Prasad Raghavendra and David Steurer from 2015. So first of all, we proved that for many polytopes associated to NP complete problems, you cannot write small semi-definite programs for them. Okay, so this exponent is really small if you're sitting in the back, but it's something like it's exponential in n to the 2/11ths. Okay, so that shows that you cannot prove P is equal to NP. And we also proved some results for approximation problems. If you consider constraint satisfaction problems, then polynomial size SDPs are no stronger. This term is undefined because we're going to define it on the next slide. They're equivalent to the power of a very specific family of semi-definite programs called sum of squares relaxations. And you'll see where it comes from in a second. And so, for instance, using that, you could show that no polynomial size semi-definite program can do better than achieve a 7/8 factor approximation to max 3 set. Okay, so assuming P is not equal to NP, famous results of Hofstad says that you can't do better than this. In this model of semi-definite programming, though, which is very powerful and is the model for designing approximation algorithms, you can say that actually unconditionally, in polynomial size SDPs, you cannot do better than 7/8. Okay, and what's the connection to quantum? So we're going to see it now. The basic idea is that starting with a small semi-definite program for some problem, we're going to find an equivalent semi-definite program of a very special form that people by different names have been studying for 20 years now. And then we'll be able to understand the model of semi-definite program through this connection. Okay? And the way we're going to do it, and this is a bit, well, you should be skeptical because like this slide would get trapped in your spam filter. It has P equals NP and quantum and there's like machine learning. I guess you guys are in a maybe, this could also be a pitch for like 100 million in venture capital funding though. Okay, so yeah, so let's try to explain now the connection and why I'm calling this quantum learning. Okay, so to do that, we need to look at some model of communication. Okay, so it's a communication problem between two parties, nothing very creative here, Alice and Bob. there's some function that they want to compute. This is a function that takes non-negative values. So this is not a 0, 1 valued function. There's some domain A for Alice's inputs, some domain B for Bob's inputs. And there's a function which is taking non-negative values they want to compute. So, and it's a very simple model of communication. Alice looks at her input. She sends Bob a message. Bob does some computation, outputs an answer. So it's one-way communication. Things are a little tricky because of the model of what it means to compute f here. So Alice can use some random bits to generate this message, and Bob can use some random bits to generate his output. And here are the constraints. Bob outputs a random number based on his input and the message that's non-negative, and in expectation is equal to the function f. Okay, so this is sort of the model of computing an expectation. So it's a sort of weaker constraint, obviously, than computing f exactly. And for some problems, it's significantly weaker. So you can think, for instance, suppose that Alice and Bob each get 2 strings, and they want to compute the Hamming distance between them. So in this model, Alice could just sample a random bit of her string, send the name of that bit and the value of that bit to Bob, and Bob can check whether it equals his value. And then output 1 if it does, and output 0 otherwise. And then it's easy to see an expectation, they're computing the fraction of bits on which their inputs differ. So with only log n bits of communication, just enough to describe the name of one of the n bits, they compute the Hamming distance in this model. So it's both maybe it's a strong model and also sometimes surprisingly weak. What's the connection between this and polytopes? So here's a communication problem given any polytope. So this is a polytope P. Think about any half space that bounds this polytope. So what I mean here, there's a pair, it's a vector, n-dimensional vector v and a number b, and I want it to be that the inner product, for every point in the polytope, the inner product with v is at most b. Okay? So v is the normal vector to this hyperplane, and b is just describing the shift along the normal direction. And then I want to also consider vertices of this polytope. And the idea is that Alice is going to get a constraint, or Alice is going to get a half space such that all of so the polytope is on one side of that half space, and Bob is going to get a vertex. And actually, for the sake of the talk, we're only going to consider polytopes where the vertices are 0, 1 to the n. So you can just make that change now. Bob gets a number. Bob gets a vector in the discrete cube, and then their goal is to compute this distance. So the distance from the point that Bob gets to the hyperplane that Alice gets. Okay? And since the point is always in the polytope, this is always the function is always non-negative. This is called the slack of that constraint. It's sort of, this is the half space gives some linear constraint, and this is how much slack there is in satisfying that constraint. Okay? So it's a non-negative function, and you can think about computing it in this model. And I guess since Microsoft is hosting the conference, I should show off some of their technology. They did that. It did that automatically. That was pretty. I didn't have to. That's not hard coded. Okay. What's the connection here? It's actually really beautiful. If Alice sends Bob an m-bit classical message, and they're able to say compute this slack function for all of the inputs, again in this model of computation expectation, then the polytope has a lift of size 2 to the m. So it's the shadow of something with 2 to the m facets. And okay, up to a factor of 2, because I didn't want to put floors and ceilings here, this is tight. So the polytope has a lift of size 2 to the m, if and only if there's an m-bit communication protocol with classical messages. What about STPs? Well, okay, so if Alice sends Bob instead an m-bit quantum message on m qubits, and they're able to solve this problem, I'll say exactly what it means to solve it in a second. It's what you would expect, but I'll write it formally. That can be done if and only if the polytope has a semi-definite programming formulation of size 2 to the m. Okay, so this communication model exactly captures the model of linear and semi-definite programming formulations for the underlying polytope. So what is this based on? It's Yanokakis' factorization theorem together with the work of Fiorini et al. To see that this holds. Yeah, so let me skip for a second. I was going to give some reason that you, okay, let me just say it anyway. So, okay, I'm not going to prove that this connection holds, but here's some intuition about why it holds, at least in the classical, in the setting of classical messages. So suppose the polytope P itself had a small number of facets. Okay, and then I want to give a communication protocol. By the way, it seems like they're trying to output some real number in expectation, so I just want to give some indication of how they could possibly exchange messages on finite numbers of bits and exactly compute that real number. So suppose this polytope P had a small number of facets. Okay, so now these green things are the normal vectors to the facets, and there's only a polynomial number. So by Farkas lemma in optimization, if I have any half space such that the polytope lies on one side of it, then the normal vector to that half space, or actually the pair v comma b, can be written as a non-negative combination of the green normal vectors. Okay, so every input that Alice gets can be written as a non-negative combination of a polynomial number of vectors coming from the facets. So what that means is that basically Alice can just, given her constraint, she can just choose one of the facets with probability proportional to its coefficient in that convex combination, and then send Bob the name of that facet. Since there are only, say, if there are only 2 to the m facets, then the name is encoded in m bits, and then Bob will just output the slack on that facet, sort of. Okay. And now you can check, since the normal vector was a convex combination of the normal vectors, in expectation they compute the correct thing. Okay, so that's, okay, and by duality this goes the other way and so on. But the point is now our study reduces to thinking about this communication problem. And just, okay, so yeah, so 2 notes. First of all, you might think, okay, there's this one-way communication model, or there's arbitrary communication. So it turns out that in this model of communication expectation, it doesn't matter. This is a result of I'm not sure I know how to say this fellow's name. You want to help, Ronald? Kanievsky? Okay, that's Kanievsky, Troily, and Ronald DeWolf showed that actually one-way communication, arbitrary communication are the same. And so, okay, so this gives you a sort of an understanding of what LP and SDP lifts are in this model. They're just reduced to questions in some communication setting. And now I want to consider a very special form of communication, okay, where Alice is a big dictatorial. I'm calling it sort of the hapless Bob. So Bob is not going to get to do anything interesting in this form of protocol. So what's the protocol? Let me describe it first classically. Bob has this bit string, okay? And let's say a k-hapless Bob protocol, or a query protocol, is where Alice just says, Bob, here are the names of some bits. I'm going to specify k bits. And here are the values I want them to have. And what you should do is look at your input in exactly those k bits. If they match those values, output a 1, and otherwise output a 0. That's what I mean by a k-hapless Bob protocol. Alice just tells Bob exactly what to do, and then he follows it and outputs 0 or 1 based on whether Alice's guess for those bits was correct or not. Okay, so it's really, Alice sends a specification of k bits, right? The number of, the length of her message needs to be log of n choose k, so it's about k log n bit message. And Bob just outputs 1 if they match and 0 otherwise. And it turns out that this special kind of protocol, if you go back to this connection, corresponds to what are called Shirali-Adams lifts of the underlying polytope. So it's a very particular family of linear programs, which we know, for instance, if you take them larger and larger, they converge to to being tight relaxations. But it doesn't really matter. They're not going to play a great role in the talk. And if Alice does the same thing, but instead of specifying k bits, she specifies k bits in superposition. Okay, I'll say what that means in a second. Then that happens. That sort of such a protocol exists to solve the problem if and only if the polytope has what's called a sum of squares lift of degree at most 2k. And again, a sum of squares lift, it's a special family of SDP lifts that are kind of generated in a formulaic way, and people have studied these for quite a while. let me just say so this is by the same paper of Kanevsky, Troy, and Ronald. And let me just say what it means for Alice to do this. Basically, Alice sends some superposition over the names of subsets of k bits and the values she wants to see in those bits. Then Bob just computes in some unitary way, whether for every thing in the superposition, was Alice's guess correct? And then Bob does say some computation and measurement that doesn't depend on his input. So the input x only comes in through Bob doing exactly what Alice told him to do, but now in superposition. Okay, so that's what it means to do it sort of with k bits in superposition. And the reason that this is sort of an interesting set of things is that while this model, especially in the quantum world, we don't understand very well, for the special case of these query protocols, actually, people have been studying this, for instance, in proof complexity, going back to Grigoriev, for 20 years. Okay, so the special case when Alice really just sends Bob k bits in the names of k bits in superposition, and Bob just sort of haplessly follows along, we understand those models very well. Okay, so now if we want to understand the general problem, because it's equivalent to understanding semi-definite programming lists of the polytope, here's a maybe naive but sort of straightforward idea. Let's try and take any quantum protocol for this problem and convert it into a protocol of this special form, where Alice just sends Bob k bits in superposition, and he just, in a quantum way, sort of computes the sort of whether she was correct in superposition, and then does some measurement. Okay, so that's the basic idea, and here's a very simple way to think about doing it. You could just try to implement some translator that gets Alice's messages, right? Alice is sending Bob some arbitrary, say, m-bit messages. You could just have a translator which translates those messages into messages for some hapless Bob, right? So like, he takes Alice's messages, he translates them into messages which just say, look in these small number of bit positions and look for the following values, and then, there's some hapless Bob sitting at the other end who just carries this out. Okay? So like if you had such a compiler which would take an arbitrary protocol or such a translator, and then if you could implement this translator in the middle and it was of high enough quality, right, then you prove that for the problem under consideration, general protocols and these query protocols are essentially equivalent. And if you go back through this model of coming from mathematical optimization, this shows that, at least for certain classes of problems, general semi-definite programs are only as powerful as these sum of squares semi-definite programs. But the point is here, though, now everything reduces to just understanding sort of, this is possibly many approaches to this problem. This is a particularly naive one. It's not clear why it should work just to implement this little translator. But if we could do it, then we would whenever we can do it, we classify the strength of this model by relating it to a communication model in which Alice and Bob are participating in some very simple interaction. Okay. So let's see. Here's one strategy for trying to implement this. This is the natural one that you might take. It's you try to be smart, and figure out what's happening. Alice is sending some quantum message to Bob, and then maybe if you look at the outputs given that message, then they, the outputs depend in some way more strongly on some bits than others, and you can try to do various clever, smart things. By the way, it's quite possible that people in this community can do it, although Toma Vidic and Raghu Mecca and I are currently working on an approach like this, and it's very difficult to be smart. I guess it's a general rule for existing in the world. It's not so easy. So we tried with my co-authors David and Prasad to be smart for a long time and failed. Okay, so here's the second strategy, which is Google apparently they use deep learning to build this AlphaGo that can beat world-class Go players, but they don't really have any idea how it works. At least that was what so maybe we can just kind of try to build Bob without really understanding what this protocol is doing. I don't know, that's what, if you read the New York Times about machine learning, it seems to be what people can do. You just do something and then you get an answer. And the hope here would be that you can design, say, a learning algorithm in such a way that the outcome of the learning algorithm is actually like, you sort of learn some simulation of, say, of Bob, and the outcome is something that happens to be hapless, like happens to be one of these special types of Bobs. Okay? So, okay, let's try to understand what that means. So it's, it says the approximation of Blob, which is an approximation to Bob. Okay, so in order to talk about this approximation problem, we need two things. First of all, how are we going to encode Bob? Okay, so you can encode Bob actually as a quantum classical state. So it sort of has two parts. One is just a classical sort of variable x, and then there's some density matrix that corresponds to the part of Bob's world that is quantum. And here's a key thing. This is actually where the size of the semi-definite program comes in, or in this model, the length of Alice's message comes in. It turns out that, if Alice and Bob successfully can solve this protocol, then Bob has nearly full von Neumann entropy. So stated in a different way, the relative von Neumann entropy between Bob and the maximally mixed state is very small. What's the reason for that? Basically, if the function they're trying to compute is relatively well spread out, then sort of on various on every x, Bob is tending to output values between 0 and 1. So the point is that Bob is actually outputting something that has a lot of entropy. So where is the entropy coming from? Well, it's coming from him, and it's coming from Alice's message. Alice's message is only m bits, so Bob must be generating the rest of it, and so that's why you get this property. Okay, but this is really where the fact that there's a short message is coming from. If we encode Bob like this, then this state has very, very high von Neumann entropy. So let's record that somewhere. And then the other notion we need is what's the notion of approximation? And I guess it's enough that Alice cannot distinguish Bob from the approximator, right? Because, if Alice, if you approximate Bob by some Bob tilde, and Alice can't figure out which one she's interacting with, or then that's the only notion of approximation that matters. Like nobody's looking at the source code of Bob to figure out if our approximation was good enough. Okay, so and if you think about it, what you can encode sort of the fact that Bob is like our approximation or any state phi is getting things correctly by a sequence of measurements that are generated by Alice. Okay, and they're elements that have the same sort of quantum classical decomposition as Bob's state. Okay, so let me go over. Okay, so let me. Okay, so here's the sort of the approximation problem. Yeah, so we have a bunch of tests that Alice is doing. You can think about it. Alice is interacting with Bob. They have to output some answers that are given, by the function f they're trying to compute. So there's a bunch of measurements she's doing of Bob's state that have to have certain values, and the measurements are all of this form. And now what you can say is, if I only care about these measurements, I don't care about the specifics of Bob and how he's implemented. I just care about having the same input-output behavior. And if my goal is really to get some Bob that's particularly simple, because I want to be able to simulate this arbitrary Bob by some Bob that does something as simple as possible, then there's this principle of maximum entropy, which says that if you're given a sequence of observations about the world, then the best hypothesis subject to those observations is the one that maximizes the entropy. And this is sort of to avoid overfitting. If you maximize entropy subject to your constraints, then it makes sense that there are, for all of the other constraints that don't say anything about the solution, you're not overfitting. You're not sort of because you're maximizing the entropy. Okay, you can think about this as a whole beautiful theory around it. So here's an optimization you can write down. Let's maximize the entropy, or equivalently minimize the relative entropy from our state to the maximally mixed state, subject to the set of tests that Alice, by interacting with Bob, subjects him to. And if you think about what we're doing, the assumption is that Bob is doing a decent job himself at satisfying this protocol. Oh, by the way, yeah, we should insist that what we get is that we can at least apply the relative entropy to it. So we insist that we get a density matrix, a positive semi-definite matrix of trace 1. Equivalently, you can think about the following. I mean, Bob is solving this correctly, so you can really say that on all of these tests, A1, A2, and so on, I want the approximator and Bob to give about the same answer. Okay? So this just says that the approximator should, in terms of input-output behavior with respect to Alice, be indistinguishable from Bob. And now you can try to solve this problem. And I guess, yeah, you could just hope. There's one non-trivial thing now that you need to do, which is a little weird, and I'm not sure anybody understands it. And in the language of SDPs, this is related to things called pseudo-densities and pseudo-expectations. There's a great theory of these things being developed, but it's still a bit mysterious what's happening there. Right? In this form, the constraints are too complicated to be able to say something about the entropy minimizer, or the relative entropy minimizer. And so we do the following. We say we're trying to approximate Bob by this k-hapless Bob, who sort of does something very simple. Alice sends him a message, and he looks at k bits in superposition and makes some decision. And therefore, if that's really the case, so if our approximator was going to be k-hapless, then it turns out that if you sort of look at in Alice's test, there's some coefficient which is the function of x. You can assume that you can basically truncate all of the high degree Fourier mass of that thing, because if Bob only looks at k bits in superposition, then actually when you take the trace, sort of, you end up averaging over all of these x's, and Bob will actually be orthogonal to everything of high degree. Because, okay, well, it's not exactly clear, but he's only looking at k things at a time. It turns out that Bob can be written as a degree at most k polynomial. So now you can replace all of if you're really hoping to get this k-hapless Bob approximation, you can replace all of the tests by low-dimensional tests. Okay, so let's just suppose you do that. Okay, and now you solve this problem. So everything was sort of formulaic. We just wrote down all the constraints, except for this weird step where we truncated all the constraints. And by the way, they're no longer measurements when we truncate them. Now they're just arbitrary symmetric matrices. Like they're not, they're not positive. They don't, yeah. And then you can compute the optimal solution of this entropy maximization problem. Okay, and one of the beautiful things about entropy maximization is that, like, the optimal solution, the form of it is this optimal solution is written in terms of the structure of the constraints. So for instance, here in this program, we didn't specify that the optimal solution should be a QC state, but it will be because all of the tests are of QC form. What happens here is basically, since the relative entropy of, basically, Bob, who we're trying to approximate, has almost full entropy, and therefore, if you think about this as a learning algorithm, it's impossible for the learning to learn too much about Bob, because there's just not that much to learn. Bob doesn't have that much information in him, and that actually allows you to bound the degree of the optimal solution. Okay, and then it turns out there's a problem here, which is that the degree you get is something like m squared, and this. Our changing of the constraints only made sense if we were going to get a degree m approximation. So this m squared is pretty bad. Let me just mention how we, okay, the m squared is bad, but it makes sense because, like, basically, there are all these degree m things that Bob is sort of, all of these tests that Bob is sort of learning about. And then Bob builds his own, you build your approximator based on these tests. So it makes sense there's some overhead in aggregating all of the information of these tests into sort of an approximator. And the overhead is reflected in the fact that we get something of degree m squared. Okay, so, but like the whole thing only made sense if Bob is m hapless. If he's m squared hapless, what we did doesn't make sense. So then this is where the symmetry of the underlying problem comes in. This is why this only works for polytopes where the vertices are 0, 1 to the n. Suppose you have a chess grandmaster and you want him to play against a bunch of chess scrubs, but it should be kind of slightly interesting. Then what do? Well, you make him play against like 100 people at once. And then even if the chess grandmaster is like m squared hapless, so like he's playing with m squared quality, split over so many games, at some point, like he's going to play one of the games at a lower level. Like, that's the hope anyway when you set this up. And so that's actually that's actually exactly what we do here. So using the symmetry of the problem, this is now we're running out of time. So but let's So you sort of you basically do this on, say, instead of doing it on n variables, do it on every possible subset of root n variables. Then Bob queries some m squared, Bob looks at some m squared bits. But if I choose now a random subset of the variables, the intersection of those variables, down here, like Bob is m squared hapless, but here on this one game, or on a randomly chosen game, actually he's only querying some small set of the bits, not m squared bits, but much smaller, because it's sort of like the intersection of this small set with a random small set. And so it turns out that here you can construct the approximator. Okay? And this is really where the symmetry of the problem comes in. That's why it only works for polytopes where the vertices are 0, 1 to the n. Okay, so that works. You get an approximator. Now you've classified the structure of sort of general communication protocols by query protocols. And therefore, you connect the general SDPs to a very special class of SDPs for which we understand things pretty well. Okay, so that solves the problem we were trying to solve. Now, here we are to the last slide. What happens, what's happening going forward? So first of all, there have been some interesting applications of this. Aram talked about one yesterday. For instance, you can say that small SDPs are bad at solving at distinguishing separable states from states that are far from separable. This application, and in fact, all of the applications of the theorem I stated here so far are by reduction. So far, nobody has opened up the proof, which I think indicates that we don't really understand exactly what's going on there. Let me mention there are two open problems which are both dying for people with experience in quantum information and quantum computation to solve them. These are sort of like the most natural open problems. One of them is we don't know what happens for instance, for the perfect matching polytope. It's still completely consistent that there's a polynomial size SDP for the perfect matching polytope, which would be a very, very interesting result for many reasons. Like matching is in P, so like there's no complexity theoretic prediction that suggests this should or should not happen. And okay, there's another open problem, which is to sort of our techniques break down for approximation problems at polynomial size to extend these to exponential lower bounds. But really, what I want to say is that these open problems they're related to basically the naivete of our approximation procedure. For instance, like we approximated Bob, but it's totally natural that like why should you just approximate Bob? Why not also approximate Alice by, say, some simpler Alice? And indeed, in the linear programming setting, this was done recently to make really fantastic progress. But in general, there's all kinds of nice things. For instance, you could ask, like, why can't you do some kind of alternating minimization in these types of things? Like you approximate Bob with respect to Alice, and you get an approximator for Bob, and then approximate Alice with respect to the approximator, and you sort of like, there are, sort of, and you get this kind of sequence of approximations. It makes sense that sort of it's easier to approximate with respect to a simpler adversary. So like this kind of alternating minimization makes sense that you might get something better. One area where I think it's, this is the last point of the talk, where I think it might have a very nice effect is in this long-standing open problem in communication complexity called the log-rank conjecture. So in the paper of Fiorini et al., they said they showed that for if you look at Boolean communication problems, so it's this model of communication expectation, but now the function is just 0, 1 valued. So you're just trying to solve problems with 0, 1 values. The log-rank conjecture is equivalent to the fact that any quantum protocol can be simulated by a classical protocol with only polynomial overhead. And what this suggests is something really beautiful. It would be nice if the problem were solved in the following way. There's, basically the log-rank conjecture says that Alice and Bob have some kind of protocol where they exchange vectors and take inner products. But there's cancellations, like the vectors can, there are cancellations they're like classical cancellations. but you can simulate that. What the authors of this paper showed is that you can simulate that with quantum communication. And this sort of leads to this kind of really nice thing, which is that I think people probably didn't think of in the sort of the classical complexity theoretic setting, that maybe the right space of, for instance, approximators of Alice and Bob is in the space of, even though it's a completely classical communication problem you're trying to talk about, maybe the right space of approximations is in the quantum space. Because maybe it's the case that like every classical approximation is actually very complex, but there are quantum approximations that are very simple, even though we tend to think of quantum things as more complicated than classical things. In the sense of entropy, it's possible that there are quantum approximators that are much more simple. It would be beautiful if you could solve the log-rate conjecture by sort of approximating Alice and Bob in the space of quantum protocols. And then, once you have these simple approximators, now you can try to convert them into classical protocols, with the idea being that the simplicity here has helped you in the final step, because you know have a very specific structure of the quantum approximator. And the existence of quantum entropy as a regularizer, as a guide in this optimization, I mean, it seems very powerful, because like in quantum you have cancellations, but still you have positivity, right? It's sort of, okay, so this is a very compelling approach, and hopefully one day someone can make it work. Let me stop there. Thank you.
Thank you. Are there questions for James? Great, we have two over here. Great, Ronald.
So what's your expectation for matching polytope?
I expect that the answer is that there is no small semi-definite program. I know that you have some partial results which suggest something non-trivial is happening, but actually those would be consistent with the fact that there's a polynomial loss in the exponent here. So I mean, something non-trivial is perhaps happening there, because because you guys have something non-trivial you can do with quantum protocols for matchings. I still think that there's no good SDP lift at the matching polytope, but the major problem is that the underlying set of vertices for the matching polytope, it's not 0, 1 to the n. It's the space of perfect matchings, and these techniques, for various reasons, fail miserably when you go out of 0, out of a product space.
Right. Thanks.
There's a question from Steve.
Can you, I didn't understand the motivation for choosing the maximum entropy estimate. Can you say maybe a few words about that slide again, please?
Yeah, so let me just, this is my favorite thing. I taught a course about max entropy. It's a simple idea, it makes sense. If you have a bunch of observations, you maximize the entropy of your subject to those, sort of satisfying those observations. So in some sense, it makes sense that since you're not overfitting, you're going to get something simple. Like this might be the simplest.
I guess the reason I'm asking is because you do wind up overfitting in a certain sense when you use a maximum entropy estimation, right? Because you wind up with like a very high rank estimate of a state. Like if you think of other problems that have natural SDP formulations like matrix completion and things like this, you use an L1 minimizer. Or you use like a least squares minimizer with an L1 regularization in order to get something low rank, which is in some sense simpler. So I'm trying to, this is why I didn't quite follow the relevant notion of simple here. Like I certainly agree a maximum entropy estimate is simple in some philosophical sense, but I'm trying to understand if it's sort of the right notion of simple for this particular problem.
So this is really about representations, because like, so L1 minimization, encourages sparsity.
Or low rank in the
or low rank in the quantum setting. The uniform distribution or the maximally mixed state, those are not sparse. They are sparse if you think about them in the right way. So in fact you can use max entropy to get sparse things, but then you have to do something like it's not naturally encouraging sparsity. Especially, really, it's, if the constraints are not sparse, you don't necessarily, like, if the constraints are saying, something dense about the space, then you don't expect that the entropy maximizer is going to be sparse. But this philosophy, but the philosophy appears really powerful. Like, I have applied it in a few settings, for instance, like an additive number theory, where you just, like, you don't understand what's happening, but you just write down your constraints and you maximize the entropy, and then you just, like, you get results that took 30 pages to prove in 5 lines. It's become a religion for me. So,
Right, and you get closed form solutions, which I guess was really useful for this particular argument. But.
Yeah, you have the power of convex programming duality to get closed form solutions. And more than that, you have the power of gradient descent. Once you have once you have this regularizer, it gives you a way to move around it. Basically, it makes the geometry of the underlying space much nicer to move around in. So in fact, like, to construct sparse solutions, you don't necessarily want to take the maximizer. You just do gradient descent, and you show that, say, the gradient update steps are simple, and the number of steps you need to get close is small, and then you get something sparse. So that's one way of getting sparse
Thank
things.
you.
Yeah.
A few other questions. I saw some hands. Maybe that answered the questions. Any other questions? Okay, if not, let's thank Jaynes again for a great talk.